she's Dr. Parvathy Prem. His topic is about the Transient Lunar Exosphere. And I have some information about Dr. Parvathy Prem. Is a postdoc researcher. Right now he's in the university, Johns Hopkins University, and Applied Physics Lab. So he's also very famous with LRO, mini RF, and other lunar orbiter instruments. Right now, he's focused on develop and apply computer method, for example, multiple colors to study the solar system body and their interaction with the space environment. And he's interested about how the atmosphere, we rarefied atmosphere near the surface, near the planetary surface. For example, the Mercury and the Moon, or the other astron in our solar system. So today she will give a talk about Transient Lunar Atmosphere. Next, we invite you to give a talk. Thank you.
Good morning, everyone, and thank you for inviting me to talk to all of you today. My name is Parvathy. I am a planetary scientist at APL in the state of Maryland in the US. I know some of you already saw me in December. So happy New Year, happy Lunar New Year. And it's good to be back with all of you. So my presentation today is about transient lunar atmospheres. So temporary atmospheres that may have existed on the moon throughout its history. And so this is really a story of the thin lunar atmosphere, how it has changed over time, and what we can learn from understanding that fascinating story. So in the background here is an image of our moon as it might have looked maybe 2 billion years ago, when we think the moon may once have had a volcanically generated atmosphere. So this is a work of imagination in the background here. This is our moon superimposed over a brief video of images taken by the New Horizons spacecraft when it flew by another moon of the planet Jupiter, Io, which is volcanically active today, like our moon may have been 2 billion years ago when life was just taking hold on Earth. So this story begins in the present day. Today, the moon, as you might know, has a very, very thin atmosphere. In fact, technically speaking, it's not an atmosphere at all. It is an exosphere, and it's a particular kind of exosphere. It's a surface-bounded exosphere, which might perhaps be the most common kind of atmosphere in the solar system. These are atmospheres that are so thin that individual molecules in the air hardly ever collide with each other as they move around. And so surface-bounded exospheres are thin by definition, but that doesn't mean that they're any less interesting. These can be very dynamic atmospheres. They interact closely with the planetary surface, so the lunar surface in this case, and they also vary over time, over a range of timescales as they respond to changes in the space environment. So changes in the solar wind flux, in the micrometeoroid flux to the surface, seismic activity, even spacecraft landings, all of these things can change an atmosphere that's so thin in observable and interesting ways. Other than the moon, our next closest example of a surface-bounded exosphere is on the innermost planet, Mercury. And there are also several outer solar system satellites, the moons of Jupiter and Saturn, which have atmospheres that are similar in some ways, but also different in other interesting ways. And the moon is the closest place where we can go to study this kind of atmosphere. The figure in the corner of this slide here is one of the early measurements of the lunar exosphere from the lunar surface. This is a chart that shows the density of argon in the exosphere over the course of the lunar day and lunar night. It was measured by a little mass spectrometer called LACE sitting on the lunar surface in the 1970s. And so you can see that in this case, argon, which is just one of the components of the lunar exosphere, varies in predictable ways over the course of the lunar day, which is of course 1 month long. But you can also see two curves here. So during the 10 months or 10 lunar days that LACE sat on the lunar surface, it also observed that some days the concentration of argon was higher than on other days, which might be related to geological activity. So even today, the moon has a thin exosphere that's dynamic and scientifically interesting in its own right. But where things get really interesting is if we start looking at how the lunar atmosphere has changed through time. And so this, I think, is maybe one of the most interesting things about the lunar atmosphere. And in fact, this whole talk is, I was thinking today, if I gave this talk 10 years ago, there wouldn't have been that much to talk about, because this idea of how the lunar atmosphere has changed over time. The basic idea has been around for many decades, but it's only recently that we've started revisiting it in more detail. So we can look at atmospheres throughout the solar system, and we can classify them in terms of the mean free path. So the mean free path is the average distance that two molecules move in the air before they collide. And now on our own home planet Earth and on some moons like Titan, the moon of Saturn, that mean free path, that distance that molecules travel before they collide with another molecule is tiny. It's only on the order of 100 nanometers. If we move to Mars, as you might have heard a few hours ago, Mars has an atmosphere that is much thinner than that of Earth. But even then, molecules only move tens of microns before they collide with each other. If we move further out into the solar system, near the edge of our solar system on Triton, Neptune's moon, the mean free path grows to somewhere on the order of a centimeter. If we move back in to the moons of Jupiter, here's Io, here's Callisto. Those have even thinner atmospheres, where the mean free path might be on the order of hundreds of meters or tens of kilometers. And then, of course, very close by, we have a true surface-bounded exosphere of the moon, where molecules can travel for hundreds of thousands of kilometers in the present day before they might encounter another molecule. But at some points in the past, the moon might have traveled along this continuum. At some point in the past, maybe a few billion years ago, the moon, it's likely experienced events that may have changed its atmosphere. So if you have a volatile-rich comet or asteroid impact or a volcanic eruption, these are events that we know took place on the surface of the moon. After events such as those, the lunar atmosphere might have looked more like the atmosphere that we see today on one of these other solar system worlds. And so the things I'd like to focus on in this presentation are firstly, to give you a brief overview of some of the processes that shape such an atmosphere. And then I'd like to talk about three different classes of potential lunar atmospheres that might have existed in the past. The very ancient primordial lunar atmosphere, and the kinds of transient temporary atmospheres that you might get from volcanism and through impacts. So there are a whole range of physical and chemical processes that shape these rarefied atmospheres and surface-bounded exospheres across the solar system. There are also a variety of source mechanisms, but this slide here really focuses on the processes. So whether you have a temporary atmosphere or an exosphere, it's ultimately this combination of physics and chemistry that makes them so scientifically rich and fascinating to study. And so there's a lot going on in this slide, but let's start here. In a thin atmosphere, molecules typically travel on ballistic collisions, so they move under gravity. They interact with the surface. So their interactions with the surface depend on surface temperature, shadows, which can vary over seasons and over the course of the day. When a molecule hits the surface, it can also stick, it can absorb to the surface for some period of time that depends on the local temperature. Molecules can also diffuse into the subsurface or undergo chemical reactions with the surface. Sometimes a molecule can land in a permanently shadowed region, which you've probably heard about earlier in this seminar series, but these are places that are so cold that molecules can stay or can be thermally stable for billions of years, for really geological timescales. If the atmosphere is thick enough, molecules can also collide. So the things in pink here are processes that are usually not important on the moon, but they can be important when the moon has a temporary atmosphere. So when there is enough air around the moon, molecules can collide. They can also exchange energy through spontaneous emission and absorption of radiation. They can also absorb radiation from the sun, thermal radiation from the surface. There are two other processes which are also important in the collisionless limit, and those are the loss processes. So the main destroyer of molecules in the lunar exosphere is the sun. Ultraviolet radiation from the sun can break apart molecules. You have photochemistry, photon-driven chemistry, and sometimes molecules can also acquire enough energy either from a collision with another molecule or with the surface, that they can escape lunar gravity altogether. So those are the two main loss processes. And so there's a whole range of physics and chemistry here. And everything that I'll talk about in the rest of this presentation ultimately ties back and is driven by all of these processes. And you can take almost any one of these little bullet points, and it is a rich field of scientific study. So we have many colleagues who study the interaction of molecules with the surface, others who study photochemistry and how the temperature of the moon changes, and each of these things is fascinating all by itself. And so now we're going to go back to the very beginnings of the moon. The first kind of transient lunar atmosphere, and probably the one that we know the least about, is the primordial lunar atmosphere. So when we talk about the primordial lunar atmosphere, we're talking about something that may have existed during the first 1,000 years or so after moon formation, around 4.5 billion years ago. This is something that hasn't been studied a great deal. And this figure here and most of the other bullet points on here are based on a relatively recent paper by Prabal Saxena at NASA Goddard. And I think as far as I know, Prabal's work is the most recent exploration of this topic. And it's an interesting one. So we have here a figure from that paper. Here is the early moon. So this is right at the beginning, very soon after moon formation, when the moon had this global magma ocean. And so the idea here is that at this time, the moon was so hot that it was outgassing volatiles, specifically heavy volatiles like the alkali metals, sodium, potassium, and silicate vapor. You had an SiO atmosphere being outgassed from this hot magma ocean. At that time, the moon was also closer to the Earth. And the Earth itself was also warm and radiating. And so the idea here is that you have this outgassed atmosphere that's heated by the early Earth, which is much closer at that point in time. And so you can have waves driven by currents in that atmosphere as it's radiatively heated And as the gas moves from the warm, high pressure region to the colder shadowed side of the early moon. And so again, at this point, there are so many uncertainties in this picture of things, but it's a fascinating period of time to think about. Some of this recent work indicates that, as you might expect, over time, within that first 1,000 years, this atmosphere gradually cooled, it gradually decreased in pressure as the magma ocean solidified and that silicate vapor became solid rock. It was likely a highly collisional atmosphere, so really an atmosphere rather than an exosphere. And one question which we really don't have answers to, but which is very interesting to think about, is what kind of traces of such an atmosphere could we see today, billions of years later? And at that point, that's a question to which we don't have clear answers, but perhaps a few years, a few decades into the future, there might be some interesting answers to that question. And so next we have a phase where we have a little more information. One of the most important geological processes that have shaped the surface of the moon that we see today is lunar volcanism. Between around 3.8 to 1 billion years ago, various regions of the lunar maria erupted. So down on the bottom here is a figure from Needham and Kring, 2017, showing which regions of the Mare basalts were actively erupting at various points in time. So this was a long period of time when there was widespread volcanism. So when you have a volcanic eruption, that not only brings magma to the surface, it also releases volatiles. So you have gases that are dissolved in that magma, and when it erupts, those gases are also released out onto the lunar surface. And so the question is, what happened to those volatiles that were outgassed? What were they, and what happened to them? And did they form a transient atmosphere? This is something there's been a whole lot of interesting work on recently. I think the first question is, well, what are these volcanic volatiles? There has been work done by Ringley and Needham and Kring, many colleagues who analyze samples and do thermochemical modeling that shows that, based on what we know about the interior of the moon, these volatiles were likely carbon monoxide gas, also sulfur-bearing species like S2, and some interesting trace species present in small quantities, but scientifically interesting, such as H2O. And these volatiles, these eruptions, I think what's most interesting about them is the range of timescales involved. Not only was volcanism active for billions of years, each volcanic eruption itself took place over the course of days. So here is a chart on the lower right from some of Jim Head's recent work, showing what such an eruption might have looked like. So you have magma ascending to the surface over the course of minutes, and then that vent and that eruption continues to evolve over the course of several days. So you have these many days long eruptions releasing quite significant quantities of these gases into the lunar exosphere, happening every 100 or 1,000 years or so for billions of years. And so these are some of the things. So from sample analysis and looking at the rates of chemical reactions and so on, we have a good idea of what this atmosphere might have been made of. But something that's very much a topic of active study is the question of how this atmosphere evolved. So I've put in a few references here, some papers that I won't talk too much about since it's not my work. But some of the questions that we've only just begun to explore, so you'll notice these were 2019 and 2021 papers, but these papers use computational models to try and address the question of, how thick were these transient atmospheres? How long did they last? So for instance, my colleague O.J. Tucker finds that depending on the quantity of volatiles released, these could have lasted for anywhere from hundreds of years to millions of years. So these could have been highly variable periods of atmospheric changes. And another question that is still a topic of active study is how effectively could such an atmosphere deliver volatiles to permanently shadowed regions or cold traps near the poles? where they can remain today. And so the next kind of atmosphere, which I'll talk about in a bit more detail, since this is based on some work that I've done, is the impact-generated transient atmosphere. If we think about all of the different sources of volatiles to the lunar surface, one of the most dominant sources was likely asteroids and comets. Over the history of the moon, asteroids and comets have very possibly delivered more volatiles, specifically water, but also other volatiles to the moon over the course of lunar history. And so what happens to volatiles after an impact? So this is something that I looked at for my dissertation work and a little bit afterwards as well. So here is, so the video that's on loop on the right here is an animation from a simulation of what happens to the water contained in a comet that hits the moon. So if you have a comet or a hydrated asteroid that hits the moon, these typically happen at high enough speeds that water, and in this, so this simulation is for H2O in particular, but in general, volatiles contained within those asteroids and comets can vaporize due to those high energies of impact, and they can begin to expand to form a temporary atmosphere around the moon. And so this simulation that's playing on this slide shows you the first 40 minutes after an impact. So you have, so in this case, you don't see the impact itself, but the simulation began with a comet that came in from the left, hit in this case, we chose to model a simulation at the North Pole of the moon, and then that comet becomes a cloud of water vapor that begins to expand around the moon. So the reason I included the simulation in this slide is to drive home the point that what happens to the vapor really depends very strongly on impact parameters. So the kind of atmosphere you get, how much of an atmosphere you get, depends strongly on things like, you know, how big was the comet or asteroid, how fast was it traveling, and what angle did it come in. Those impact parameters are really important. And those determine how much of that water remains gravitationally bound. So in this case, the colors here show you the speed of that vapor. And now escape velocity on the moon is around 2,300 meters per second. And so you'll see that a lot of this vapor that's released is going so fast that it escapes the Earth-Moon system. But some fraction of it is traveling more slowly, and it remains held by gravity around the moon to form a temporary atmosphere. And this continues to evolve even beyond that initial 40 minutes. So this animation here is a slice through the atmosphere, showing you, this time the colors indicate the gas density in units of the number of molecules per cubic meter. And this animation on loop here shows you the evolution of that vapor cloud over the course of hours. I think in this case, it's from around 1.5 hours to 6 hours after the impact. And so there are several things that really pop out in these simulations. And a few that I wanted to highlight is, well, one thing is we have again this question of how long does such an atmosphere last? And in this case, we think that impact-generated atmospheres might last for several lunar days. So maybe not as long as volcanic atmospheres, certainly not as long as the primordial lunar atmospheres, but they can last for several lunar days. And they also have this certain characteristic structure. Vapor expands out and then it falls back and then it moves around in characteristic ways. And so the behavior of that transient atmosphere is what affects how much water remains gravitationally held, and also how much of it is lost to space and how much of it is ultimately deposited near the North and South poles. And so if we come back again to our big picture view, here is the lunar atmosphere through time again. So if we sort of connect those three kinds of atmospheres and look at them in context, here's the picture that we get. So this is a sketch of pressure as a function of time, and I haven't put any units here because we really don't know what the precise values were. But in general, we think there was first an epoch where the moon had this thick primordial atmosphere that gradually decayed over time. We then had a second epoch when the atmosphere was still decaying from its primordial state, but then you had volcanism occurring at certain intervals. Early on, in this second epoch, you had the really large impacts, and the size of impacts likely declined with time. And then we reached the present day, where the lunar atmosphere is usually very thin, but sometimes you can still have these impacts that can raise the atmospheric density temporarily before they gradually decay. And so each of these processes is still an active area of study. And one of the questions that is very much worth asking in order to understand these atmospheres further is to ask the question of, well, how can we possibly learn about these atmospheres today? What traces of these atmospheres remain on the lunar surface today? And so in my second final slide, I wanted to share with you an attempt at trying to piece together some of the pieces of the puzzles. So almost everything in here, there are still uncertainties regarding many of these things, but here's what we think we know. We had these three classes of atmospheres that existed at different points in time. We think they varied in different ways, and that affects what we might try to look for in the geological record today. So first of all, they differed in composition. The primordial lunar atmosphere was likely very heavy volatiles. Volcanically generated atmospheres were mostly carbon monoxide and sulfur-bearing species, with some other interesting trace volatiles. Impacts, asteroids and comets can deliver H2O, CO2 are some of the more common volatiles. Organics can also remain in the atmosphere and can condense at low temperatures near the poles. These atmospheres also varied in their duration and their density. The thickest and perhaps the longest lived was the primordial atmosphere, which lasted until the magma ocean cooled after 1,000 or a few thousands of years. Volcanically generated atmospheres, the question of their duration is still actively debated. They could have lasted anywhere from hundreds to millions of years, depending on the scale of the eruption. And these were, could be initially quite thick, quite continuum, and then they gradually decay to something more rarefied. Impact-generated atmospheres are the shortest lived, and for most impacts, other than the very large ones, they're mostly very thin, rarefied atmospheres. And then we get to the interesting question of, well, how can we see evidence for any of these today in the geological record? The primordial atmosphere, we don't yet have samples from the lunar far side. Those could be some key pieces of evidence when it comes to understanding this primordial era. Such an atmosphere such as this could result in differences perhaps in surface composition and in differences between the near side and the far side. If the near side was heated more strongly by the hot early Earth, this is really quite a wide open question at the moment. Evidence of volcanism and volcanic volatiles are preserved in pyroclastic deposits, which are these beds of glass beads strewn near volcanic vents. Those have been observed in remote sensing data. So pyroclastic deposits and the volcanic glasses that they contain preserve some traces of those volatiles. And then some volatiles that might have been more widely distributed may have been deposited at the north and south pole of the moon and may be present there today. So by looking at the composition of polar volatiles, we may be able to see some traces of ancient volcanic atmospheres. Similarly, impact-generated volatiles also migrated to the poles in all likelihood. And there's also been some recent work by my colleague at APL, Tarek Daly, who carried out some impact experiments and found that, a lot of the water contained in a comet or asteroid can actually be preserved in impact glasses near the crater. So when the asteroid hits, some of the volatiles contained in that asteroid travel very far, often to the poles, but some can be trapped in the vicinity of the crater in some of those glasses that are formed by the heat of the impact. And so I wanted to leave you with a couple of thoughts. The first is that the lunar atmosphere is fascinating in its own right, but it's also connected to a whole bunch of other problems across the solar system. So for instance, we know now over the course of the past decade that Mercury has polar deposits of water ice and perhaps some organic compounds, some dark volatiles that haven't been identified yet. But we think that Mercury's polar deposits might have been delivered by a volatile-rich impact. And so understanding impact-generated atmospheres has consequences not just for the moon, but also for Mercury. When it comes to understanding lunar volcanism, volcanically generated atmospheres, we have a very interesting analog in the outer solar system moon, Io. Io today looks perhaps very much in some ways like the moon looked several billions of years ago. Of course, Io's surface looks very different. It's further out in the solar system, but in that it is a volcanically active moon with a thin atmosphere, there are interesting similarities there. And the moon the primordial moon might also be an exoplanet analog. So the Spitzer Space Telescope, among others, has recently begun to discover these small rocky exoplanets that are very intensely heated. Some of these are about the same size as the moon. And so if we can understand the primordial lunar atmosphere, that might teach us something about rocky exoplanet atmospheres, very far away beyond the solar system indeed. And then, lastly, even though we don't have a thick lunar atmosphere today, we still have the contemporary lunar atmosphere. Understanding even the thin atmosphere that the moon has today is an excellent way to understand surface-bounded exospheres all across the solar system. And also, if we can understand the processes that shape that atmosphere, we can extend those back in time and understand how the atmosphere has evolved over time. So with that, I have a few references here, and I will send the slides via email to Professor Ip and Professor Kuo so that you have these links. But that is all I have for you today. And so if we have time for questions, I would be happy to take any questions. All questions are good questions. So don't be shy. And if you think of questions later, feel free to email me as well.
Yes. I have a question.
Yes. Sure.
In your simulation for the impact, but could you explain how many waters will be generated by the impact rate? Related to the impact rate.
Yeah. So, so the simulation I showed, that was for a 2-kilometer comet composed of pure water ice, which is an assumption. So for that single impact, we found that around 1% of the total water was deposited near the poles. If you integrate that over time, so we have not just this one impact, we have many impacts happening over billions of years. If you integrate over time, you end up with a number of something like 10 to the power 12 kilograms. And so that's quite a high number. So so it certainly seems that impacts could deliver a great deal of water to the poles. And so it's a little bit of a mystery. If you have so many impacts and they're all delivering so much water, then where is the water today? So it seems that there is still some things that we don't quite understand about the other processes that operate after water is delivered. So you have water deposited, but then there are these different loss processes. So you can have you have energetic particle sputtering, micrometeoroids can vaporize ice, and then we also think that the lunar poles might have shifted over years. So some places that are cold today may have been warm in the past. So so based on the simulations and looking at the flux of impactors and the size distribution and so on, we find that impactors could certainly deliver enough water to explain, for instance, the hydrogen that we see at the North and South poles. But perhaps the reason that we don't see all of that water today is likely due to the loss processes, and those are still an area of active investigation. Thanks for having me, and enjoy the rest of your day.